Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to week 3 of our course, and as you know, the title of this week is the nanotransistor, which, as I mentioned in my first lecture, is probably one of the most important devices, one of the most important electronic devices. And like every laptop you buy has over 1 billion of these nanotransistors in it. But I should state right in the beginning that what we'll be doing this week won't really make you an expert on nanotransistors, not even close. Because, for that you need to take the course next semester that will be offered by my colleague Mark Lundstrom, who is the real expert on this subject. Here in this course, what I'm using the nanotransistor for is to illustrate some basic principles in terms of understanding how current flows in small devices. So, as I had mentioned earlier, that basically a transistor is like a resistor, in the sense you have this channel with two contacts, which you call the source and the drain. And when you apply a voltage across it, like connecting a battery across it, a current flows. And the voltage divided by the current is what you'd call its resistance. And for small voltages, I guess the current is proportional to the voltage, and you can talk in terms of the resistance. And what you have done so far is to discuss the factors that affect that resistance. Now, a transistor, however, as I had mentioned before, it's a 3-terminal device. There is a third terminal that allows you to control that resistance. So, what I'm going to show here schematically is this third terminal. That is, here is the actual channel where the electron flows. And you have an insulator. And I'm kind of showing it schematically as just here. But actually, if this is the channel, then the insulator could be all across it. Or sometimes they construct it with the insulator all around the channel. So those details we are not getting into, because as I said, the whole purpose is to understand some of the basic principles here. So that's this insulator, and you apply another voltage to this insulator. And to distinguish between the two voltages, now that we have two of them, one of them is called the drain voltage, as you might expect, because that's the voltage that's applied to the drain. And the other is called the gate voltage, because this third terminal is called the gate. So those are the two voltages, and their purpose is very different. The drain voltage, like the voltage we talked about before, it causes current to flow in this channel. Whereas in this gate terminal, ideally, no current should flow. In practice, there is some leakage current, which for most of our discussion we'll be ignoring anyway, although these days that is getting to be significant. But ideally, there shouldn't be much current here because there is this insulator. And its sole purpose is to control the current flow. Now, how does it do that? Well, the way it works is something like this. As I had mentioned before, that in order to understand current flow, the first picture you draw is, this axis is energy, and you try to draw the availability of states at different energies. And that's what you usually denote by this density of states. And I've shown just a schematic here. And the basic concept that we discussed earlier is that how much current flows or what resistance you get depends on the availability of states right around the electrochemical potential, right here. And what the gate voltage does is to move these density of states relative to this electrochemical potential in the contacts. So let me explain this point a little further. That earlier what I had said is that when you put a drain voltage on the drain, what it does is it lowers all the energy levels in the drain so that you have a different electrochemical potential here. It's mu2. So what this drain voltage does is to control the energy levels here relative to the source, and when you put a positive voltage, everything goes down. And the amount by which it goes down, that depends on this drain voltage, like we had discussed. Now, the purpose of the gate voltage is to move all the energy levels in this channel region relative to the two contacts. So we could either say that a positive voltage on this moves everything down. So instead of the way I have drawn it currently, if you put a positive voltage there, it could all go down somewhat, for example. And this would also go down. And as a result, the resistance would change. The amount of current flow would change because right around the chemical potential, the states that you have, all that is changing. So that's the general principle of how the gate voltage controls the current flow. On the other hand, if you put a negative voltage there, then you could raise everything up. You could do the following. That instead of going down here, it could be going up here. And as you can see, with enough negative voltage, you could be pushing it above the electrochemical potential. So for example, you could even make it look something like this. And in that case, there would be no current flow because now the electrochemical potential would be in the gap, no density of states there, no current would flow. So that would be the off state of the transistor. As I mentioned before, a transistor, it changes this conduction, the resistance, by orders of magnitude, like by a factor of 10,000. So when it is in this, along this black curve, you might get a lot of current flow. The resistance may be, say, 10 kilo ohms. On the other hand, once you have put a negative voltage and pushed it up there, there's hardly any states here, and the resistance could be, like, as I said, 10,000 times bigger. That would be like hundreds of mega ohms. And that's the basic principle of this transistor operation. Right? Now, so when discussing the operation of a transistor, the picture that often people draw is this current versus voltage. And I guess it would look something like this. I versus V sub D. So now you have two voltages, so you have a choice. You could either plot current versus drain voltage or current versus gate voltage. And both are done. So what I'm trying to show is what it would look like, the current versus drain voltage, keeping the gate voltage fixed. So what you'd see then is, for low drain voltage, current is proportional to the voltage, and so you see something increasing linearly. And if you looked at the slope of that, that would give you the conductance that we talked about. That's kind of what we have been focusing on in the first 2 weeks. But then if you increase the voltage further, what happens is it actually levels off. Indeed, ideally, what people would like it to do is essentially saturate. Because if at high voltages the current becomes independent of voltage, that helps build circuits with these devices for reasons that we are not going into. But ideally, you would almost like it to give you a current that's independent of the voltage. But in practice, what you get is a certain slope to it. So the current increases, but not quite as fast as it used to. In fact, one of the problems is that as you make transistors smaller and smaller, it is harder to make this slope to control this slope. It wants to get bigger. So this is the current versus drain voltage for a fixed gate voltage. Now, with a different gate voltage, something more negative, you might get less current. It would look something like this. So this would be with a negative gate voltage. The current would be less. Now, if you are interested in the slope of I versus V around here, that is what you'd call the low bias conductance or linear response. And that is what we have talked about for 2 weeks. And this week, as I said, I won't really be telling you enough about nanotransistors to do justice to this subject. My purpose is mainly to use nanotransistors as a way of illustrating what happens and the kind of factors that you have to worry about at high voltages. That is, why is it that this current levels off, for example? Okay? So that would be the first question, that why doesn't the current just keep increasing like so? Why does it level off? Now, for that purpose, you might want to look at the expression for the current that we first obtained back in week 1. You see, we had this expression first, and then what we had done was we took this part of it and said that for small voltages, it is proportional to the voltage. So we said that if the difference between the two chemical potentials is small, then you could write this as minus derivative of F with respect to E times the applied voltage. And that then gave us an expression for conductance, which is like, because the current is then proportional to the voltage. Now, what we don't want to do is make that approximation in this case, because this approximation would only apply down here. Whereas what we're really trying to understand is this full thing. And so, for what we'll be discussing this week, we won't really be making that approximation at all. We'll go back to the original expression. And then the question is, well, what is the current we expect when the voltage has been increased quite a bit? Okay. So for that purpose, let me that picture over here again. Yeah, I guess that would be good. Draw this picture here. That we have this is E, this is D of E. So what I've plotted here is density of states. As you know, this conductance depends on is proportional to the density of states. There are other factors we have discussed. So actually what you want is this conductance function, which would look qualitatively at least like this. Okay. And F1 is determined by the electrochemical potential in this contact, that's mu1. And F2 is determined by the location of the electrochemical potential in the second contact. And if you remember, the Fermi function looks like, as we had done, that around mu1, it changes from 0 to 1. And on this side then, usually we have restricted ourselves to small voltages where mu2 would be just around here. But let's assume that we have put a fairly big voltage. Okay. So mu2 is, let's say, down here. So now the question is, as I keep increasing the voltage, of course this keeps going down, what will happen to the current? And this is where you can see that, well, current of course flows in this energy window between mu1 and mu2, because this is the region where electrons keep coming in from here and keep getting pulled out over there. And so you'd say, well, as I pull this down, more and more of the energy window becomes available for conduction, and so I should get more and more current. And that's kind of true. You keep lowering it and it should keep going, keep increasing. And then once the mu2 drops below the bottom of the band, the current should just stop increasing anymore. Because now it really doesn't matter where mu2 is here or here. Basically, all you have for current flow are these energy levels. So no new levels are being made available by lowering it any further. And so what you might expect, if this was the whole story, then what you might expect is that a current versus voltage would look like to increase and then just level off. Why? Because as I keep pulling it down, once it drops below the band edge, there is no new levels coming up. That's what you'd expect. Now, that is not the correct story, though, because, you see, if that was the whole story, then, currents would saturate. As I mentioned earlier, that's exactly what you'd like it to do, except that you usually have to work very hard to make that happen. This almost sounds like that's the natural thing to happen. So that's not the case. And what have you missed in this picture? Well, what you have missed is we are assuming that when you put a drain voltage on this, all that happens is that this mu2 keeps going down. What also happens, though, is that this channel itself also gets pulled down somewhat. So when you so let's say this is our reference, this is 0. And let's say I've put 100 millivolts here. And so because of the 100 millivolts, of course, everything in the drain is going down. But the channel also has some effective potential, see, which I could denote as, say, U. U being the potential energy in the channel. And when I put 100 millivolts there, not only does the drain go down, but also this one goes down somewhat. And that needs to be taken into account. Because, you see, when I pull this thing down, I earlier argued that when you pull it down, at some point the current will stop increasing. Why? Because, well, after all, there's no new states being made available. But that's not true. What really happens is that when you put 100 millivolts here, some fraction of it also goes to lowering these levels. And so actually you now have more states available to do that. And this fact needs to be included in our current equation here. So the current equation that we did back in week 1 did not account for this fact. And which was fine because we are looking at small bias, didn't matter. But if you want to understand high bias, if you use this equation, you will predict that the current saturates perfectly, which is not quite correct, as I mentioned before. One has to actually work very hard to make that happen. Okay? And in order to have a model that will predict correctly how the current keeps increasing at high voltage, we need to change this somewhat. And how you change it, that's what we'll talk about in the next module.